Provisional patent disclosure. Twisted-Tendon Piezoelectric Artificial Muscle Actuator. Inventor, Chris D. Seely. Date, August 17, 2026. Docket, working title, Dual Drive Twisted-Tendon Piezoelectric Artificial Muscle. 1. Field of the invention. This disclosure relates to linear actuators for robotics, prosthetics, exoskeletons, and adaptive structures, and more specifically to a tendon-based contractile actuator driven by opposed piezoelectric rotary drives and enclosed in an elastomeric compression housing that provides passive elastic energy storage, impact damping, and self-centering return force. 2. Background. Twisted string actuation is a known technique in which a flexible cord or bundle of cords is twisted by a rotary motor, causing the bundle to shorten in length and increase in diameter, converting rotary motion into linear contractile force. Conventional TSA implementations typically use a single electromagnetic DC motor at one end of the string, anchored at the opposite end to a fixed point or load. Conventional TSA designs share three limitations this disclosure addresses. Electromagnetic motors draw continuous holding current to resist backdrive under load, since they are not inherently self-locking. A single-ended twist source requires the full contraction to be generated by one motor, limiting force and contraction speed for a given motor size, and the twisting bundle is typically exposed, offering no passive energy return, impact protection, or housing integration. 3. Summary of the invention. The invention is a self-contained contractile actuator module comprising 2 piezoelectric ultrasonic rotary actuators, one mounted at each end of the module, each with a rotor-stator pair capable of producing continuous rotary twist output and inherent friction-based self-locking, a quadruple tendon set of 4 high-strength fiber tendons arranged in a cross pattern, anchored to the rotor of each opposing drive and passing through a central through hole in each stator, such that opposite rotation of the two drives twists the tendons together into a single tightening rope-like bundle along the module's central axis. A semi-transparent elastomeric compression housing enclosing the tendon bundle between the two drives, sized so that as the tendon bundle shortens and increases in diameter under twist, the elastomer is radially compressed and bulges outward, storing elastic strain energy. A control scheme in which driving the two rotors in opposing rotational directions contracts the module, and energizing the drives allows the self-locking drives to hold the contracted position with elastic give, or allows a commanded reverse rotation to unwind the tendons, whereupon the compressed elastomer's stored energy assists in rapidly returning the module to its extended rest length. The combination of a dual-opposed self-locking piezoelectric twist source and an elastomeric housing doing double duty as compression spring, energy return element, and protective shroud is believed to be novel relative to conventional single-motor, unhoused TSA designs. 4. Detailed description. 4.1 Drive units. Each drive unit is a piezoelectric traveling wave rotary actuator consisting of a stator and a rotor. Because ultrasonic piezoelectric motors are friction-driven rather than driven by a magnetic field acting across an air gap, they exhibit high holding torque at zero input power. The rotor resists back drive through static friction at the drive interface rather than through continuous current draw. This property is the physical basis for the module's power-off position holding behavior. 4.2 Tendon set and twist mechanism. 4 tendons of a high tensile strength fiber are arranged in a cross pattern between the two rotors and pass through a central through hole in each stator for anchoring. When the rotors are driven in opposing directions, the tendons wind around each other along the module's central axis, converting rotary displacement at each end into axial contraction at a mechanical advantage set by the instantaneous winding radius of the bundle. Driving both ends simultaneously approximately doubles the effective twist rate and available torque compared to a single-ended TSA of equivalent drive size. 4.3 Elastomeric compression housing. A semi-transparent elastomer sleeve encloses the tendon bundle along its full length between the two stators. As the tendon bundle shortens and its diameter increases under twist, it radially compresses the elastomer, which bulges outward and stores elastic strain energy. On release, this stored energy contributes to unwinding the tendon and returning the module to rest length, reducing the mechanical work the drives must perform on the return stroke and providing passive shock absorption against axial impact loads during the module's rest-off state. 4.4 Operating Cycle. Rest, off. Drives unpowered, tendons unwound, elastomer uncompressed, module at full extension, module holds position with elastic give under external load. On contract, drives energized and rotated in opposing directions, tendons wind into a tight rope, elastomer compresses and bulges outward, module shortens and stores elastic strain energy. Off, release. Drives de-energized or reverse-driven, stored elastic energy in the compressed elastomer and wound tendon assists rapid unwinding, module returns toward rest length. 5. Advantages over existing ART. Power-off position holding via inherent piezoelectric drive self-locking, without a separate mechanical brake. Dual-opposed drive configuration increases available contraction force and/or speed for a given individual drive size versus single-ended TSA. Integrated elastomeric housing performs 3 functions simultaneously rather than requiring separate components. Passive elastic energy storage and return reduces electrical work required on the release stroke and provides built-in mechanical impact absorption. Scalable force output via tendon count, tendon material, and drive torque selection for a given application. 6. Additional embodiments. 6.1 Self-lubricating ball-end tendon terminations. In a refinement of the tendon said described in section 4.2, each tendon terminates in an integrated low-friction ball end at its anchor point to the rotor. This converts the sliding, rubbing contact at the tendon anchor and stator through hole from a high-friction abrasive interface into a low-friction rolling or pivoting interface, directly reducing the wear mechanism expected to be the primary limit on cycle life. 6.2 Auxiliary spring augmented elastomer housing. In a refinement of the elastomeric compression housing described in section 4.3, one or more discrete mechanical springs are embedded within the elastomer, arranged concentrically or longitudinally around the tendon bundle. The auxiliary springs supplement the elastomer's intrinsic stiffness, allowing the module's force, displacement characteristic to be tuned independently of elastomer material selection, of particular value in industrial applications requiring a defined temperature-stable stiffness profile beyond what the elastomer alone provides. 6.3 Vacuum-assisted holding chamber. In a further refinement, the elastomeric compression housing is sealed to form one or more interstitial chambers around the tendon bundle. As the tendon bundle twists, thickens, and shortens during the contraction stroke, the enclosed air volume in the sealed chamber is displaced. Venting a metered quantity of this displaced air through a needle valve or check valve during the contraction stroke both sheds a portion of the heat generated during actuation via convective purge and leaves the chamber underfilled relative to its subsequent expanded state. On the following extension stroke, as the chamber's enclosed volume increases while the vented air is not fully replaced, a partial vacuum develops within the sealed chamber. This partial vacuum produces an axial holding force proportional to the pressure differential in the chamber's cross-sectional area. Given typical chamber cross-sections, this force is expected to be modest relative to the tendon-driven contraction force, and is therefore intended primarily as a redundant, zero-power fail-safe holding mechanism, supplementing the piezoelectric drive's inherent self-locking and the elastomer's elastic return force so that failure of any single holding mechanism does not by itself result in uncommanded loss of position, rather than as a primary source of holding or actuation force. The primary purpose of the metered venting described above is thermal, shedding heat generated during the contraction stroke via convective air exchange. Controlled release from the vacuum-held state is achieved by admitting a small, metered volume of air through the needle valve, check valve assembly, breaking the seal and permitting the module to move freely on the next actuation stroke. 6.4 Conductive seal surface as integrated position, state sensor. In a further refinement, the sealing surface of the vacuum-assisted holding chamber described in section 6.3, the surface pair that makes and breaks contact as the chamber seals and unseals, is rendered electrically conductive and electrically isolated from the surrounding structure. Electrical continuity across this surface pair then provides a normally open, normally closed binary signal indicating the module's sealed, unsealed state, usable by a control system as an integrated position sensor and as a means of detecting seal degradation over service life, e.g., a mismatch between commanded state and sensed continuity indicating a failing seal, without requiring a separate limit switch, encoder, or other discrete sensing component. 6.5 Bidirectional thermal conditioning. In a further variant, the needle valve, check valve gas path described in section 6.3 is operated in reverse to admit heated gas into the sealed chamber surrounding the elastomeric compression housing. Rather than venting for cooling, in order to maintain the elastomer above its glass transition temperature and preserve its flexibility and sealing function in extreme cold environment service. Because a true space vacuum environment provides no ambient atmosphere from which to draw makeup gas or into which to vent, this variant employs a sealed, self-contained gas reservoir and associated heating element in place of the vent-to-ambient arrangement used in terrestrial service, while retaining the same valve architecture described in section 6.3. Elastomer material selection is a complementary, non-exclusive means of extending cold environment service range and may be combined with this variant. 6.6 Guided variant for solenoid replacement applications. In a further variant intended for industrial linear actuation applications, a central shaft passes axially through the module, around which the tendon bundle twists. The shaft constrains the tendon bundle against buckling or lateral deflection under transverse loading and guides the module's linear stroke, allowing the module to function as a direct mechanical replacement for an electromagnetic solenoid in guided linear actuation applications, providing comparable stroke speed and guided motion without the continuous resistive heating of a solenoid coil, since the module's holding state is passive rather than requiring sustained coil current. 6.7 Design principle, minimizing duty cycle. The module is intended to be operated so that it spends the substantial majority of its service life in a de-energized holding state, with active electrical drive reserved for the brief transition strokes between states. Stored elastic energy and, where implemented, stored vacuum potential are treated as the primary means of maintaining position, with the piezoelectric drives used only to add or remove energy at state transitions. This principle is expected to be the primary lever for managing the thermal limitations discussed in section 7. 7. Known limitations and areas requiring development. This section is included to accurately scope the disclosure and should be refined as prototyping proceeds. The module produces contraction force only, it cannot actively push. Bidirectional force output requires pairing two modules in an antagonist configuration, as in biological flexor-extensor muscle pairs. Continuous high-frequency actuation is expected to be thermally limited by piezoelectric drive efficiency. Sustained high-duty cycle operation is likely to require active thermal management, whereas burst, intermittent operation at low-duty cycle should be thermally self-limiting with passive heat sinking through the stator housings. Tendon fatigue life at the through-hole pass points is expected to be the primary wear limiting factor. Cycle life claims should be validated against the specific fiber material and guide, bushing design chosen rather than assumed. Full stroke response time is governed by the number of drive revolutions required and is expected to be substantially longer than the drive's electrical response latency. These two figures should be specified separately in any final claims. The vacuum-assisted holding chamber is intended primarily as a heat-shedding mechanism and secondarily as a redundant fail-safe holding feature, not a primary force source. It depends on long-term seal integrity at the interface between the flexible elastomer housing and the rigid stator end caps. Elastomers are gas permeable and this seal will undergo the same cycle count as the rest of the module. Vacuum holding performance and the conductive surface sensing signal over rated service life should be validated empirically rather than assumed. The cold environment thermal conditioning variant requires a sealed, self-contained gas supply for true vacuum space service, since no ambient atmosphere is available to draw from or vent into. The added heater, reservoir, and valve components introduce their own failure modes that should be weighed in a materials systems trade study against alternatives such as direct conductive or resistive heating of the housing. 8. Potential applications. Robotic actuation, prosthetic and orthotic devices, exoskeletons, haptic feedback devices, adaptive, shape-changing structures. 9. Preliminary claims. 1. A contractile actuator comprising 2 rotary drive units, each comprising a stator and a rotor and configured to hold rotor position. Without continuous electrical power via inherent friction-based self-locking. A plurality of flexible tendons arranged between and anchored to the rotors of the 2 drive units in a cross pattern, and passing through a through hole in each stator, wherein rotation of the 2 rotors in opposing directions winds the tendons into a twisted bundle, shortening the axial length of the actuator and increasing the bundle's radial dimension. 2. The actuator of Claim 1. Further comprising an elastomeric housing enclosing the tendon bundle between the 2 drive units, configured to be radially compressed by the increasing radial dimension of the tendon bundle during winding, thereby storing elastic strain energy usable to assist axial extension of the actuator upon unwinding of the tendons. 3. The actuator of Claim 1, wherein the rotary drive units are piezoelectric ultrasonic traveling wave motors. 4. The actuator of Claim 1, wherein the tendons comprise a high tensile strength synthetic fiber cord. 5. An antagonist pair of actuators according to Claim 1, arranged to provide bidirectional force output at a shared load point. 6. The actuator of Claim 1, wherein each tendon terminates in a self-lubricating ball end at its point of anchorage to a rotor. 7. The actuator of Claim 2, further comprising 1 or more mechanical springs embedded within the elastomeric housing, arranged to supplement the elastomer's stiffness. 8. The actuator of Claim 2, wherein the elastomeric housing is sealed to form at least 1 interstitial chamber around the tendon bundle, and further comprising a needle valve or check valve configured to controllably vent and admit air to and from the chamber, such that a partial vacuum developed within the chamber during operation contributes an axial holding force to the actuator. 9. The actuator of Claim 1, further comprising a central shaft passing axially through the tendon bundle, configured to guide the bundle against lateral deflection and to guide the actuator's linear stroke. 10. The actuator of Claim 8, wherein the sealing surface of the interstitial chamber is electrically conductive and electrically isolated from the surrounding structure, such that electrical continuity across the sealing surface provides a signal indicative of the actuator's sealed or unsealed state. 11. The actuator of Claim 8, further comprising a sealed gas reservoir and heating element configured to admit heated gas into the interstitial chamber to maintain the elastomeric housing above its glass transition temperature in cold environment or vacuum service. These claims are a starting point for attorney drafting and have not been vetted for prior art beyond the general TSA literature referenced in Section 2. A formal prior art, freedom to operate search is recommended before filing. 10. Figures. The following figures are schematic and intended to illustrate the arrangement and operating principle of the components described above. They are not to scale and are not intended to limit the disclosure to the specific proportions shown. Reference numerals. 10. Stator housing 12, rotor 14, quad tendon set 16, elastomeric compression housing 18, through hole 20, self-lubricating ball end tendon termination 22, auxiliary spring embedded in elastomer housing, sec. 6.2, 24, sealed interstitial chamber 26, needle valve, check valve 28, conductive sealing surface, no NC state sensor contacts 30, center guide shaft 32, rotor rotation direction.